talking about a limit. The verbal way to describe a limit is as x approaches some number in a function, what does the outcome or the y value or the function value get closer and closer to? You could approach any number from above or below, and all those words then, thankfully, can be shortened up a ton with math notation. Math notation is meant to confuse you or to look intimidating. It's meant to summarize a ton of words into a little bit of writing. So this then is, you could say, as x approaches a from the right, what does y approach? Or the function approach? From the positive side of it. This is x approaches from the left, or the negative side of the number line, I guess you could say. Then there is the limit. As x approaches, if there's no little sign up there as far as from the right or the left, then it's as x approaches from the right and the left. If the one-sided limits are equal, then that number that they approach from the left and the right, that's your answer, okay? That's the answer. So if the graph approached 2 from the left, 2 from the right, then the limit, left and right, is 2. Okay? But if it's a case where the one-sided limits don't agree, they're not equal, then the limit, what? People who have seen this before? Does not exist. You may abbreviate that DNE. That's in my class and on the AP. They do. I mean, that's universal. I don't know about universal. Oh, American. Right? I've never done calculus in Germany. Maybe it's, I don't know. But in America, anyway, DNE is acceptable for does not exist. All right? Understanding this from a graphical level. Remember yesterday we talked, I think I talked about the rule of 4. You understand math on 4 levels. Verbally, which is all this writing stuff. Graphically, which is what we're about to do. Analytically, which is if you have an equation, no graph. Or numerically. Now the table-wise, I'm not sure if Ms. Cannon or your pre-calc teachers hit the table. I think it's important, so I'm going to hit numerically today as well. We'll get to that in a second. But first graph. Okay? The limit as x approaches 0 from the left. The first time through, we'll go through slow. So wouldn't you agree that if we do this graphically, we go to the x part of the number line and locate where we're approaching. Here's 0. And then you decide, go from the left or the right. Wouldn't you agree that this is approaching 0 from the left? So that means a little less than 0. After you do that, then you actually go to the curve and trace along until you get to an x of 0 and say, what are those y values approaching? And what are the y values approaching as x approaches 0? 1. Excellent. All right? Now, on B then, if you are approaching 0 from the right, then the right means points on this curve. And if you get on that line closer and closer to 0, let's get some participation here. Colin, if you approach 0 from the right, then what do the y values approach? 4. Excellent. What about the fact that that circle, though, is not filled in? Is that a problem for the limit? Why? Because the limit is all about the approach. Yeah, it's all about the approach. Now, when we talk continuity, is the at important also? It is. But for limits, it's all about the approach. And I think you'll agree that these y values are hitting 3.9, 3.99, 3.999. Those are getting closer to 4. I don't care about the at 4 or at 0 is not there. I don't care. It's about the approach. All right. What about the limit then, Alexander? If the left-hand limit was 1 and the right-hand limit was 4, then what about the limit? does not exist, and we may abbreviate that D&E. Now, there are going to be times when I'm going to ask you to justify that, but I will make it clear in the problem, you must justify your answer, or if you say D&E, justify, in which case you would say D&E because the one-sided limits aren't equal, or because if you have those already found, you could say because 1 is not equal to 4. We'll practice that a little bit, all right, the justification statement. Now we're approaching 2 from the left. So here's 2. Forget the point, it's about the approach. So from the left is more like 1.9 and so on. That's this curve. And tracing towards 2. So Tyler, as you approach 2 from the left, what are the y values approach? 3. I agree. Are there any questions on that? Okay, as you approach 2 from the right, Mr. Coco, are you here today? Anybody looking around seeing him? I don't know what he looks like. Okay. All right, so he's not here. How about Radhika? Oh, didn't say that right. Did I? All right, as you approach 2 from the right, what do you say? 3, yeah. Here's from the right, I'm on the curve, and those are getting closer and closer to 3. So what about the limit at 2, Heather? It's also 3. In this case, the one-sided limits agree, and therefore the limit does exist. The left, the right, it's all 3. Okay? Now, surely you're, at some point, I was always thinking, what about the point being empty? That's got to be a thing. It's got to be something. Well, when you talk about the actual at, then that's what this question is a reference to. What is f at 2? In other words, forget the approach, where's the dot? And so what is f at 2? 1. That's when that point means something. What about f at 0? Yeah, it's not a very hard point, but it is solid there, and so it is. All right. So that's a graphical, that's the expectations for being able to read a graph and do it. Is that cool? Usually that's pretty good for students. Okay. Let's go with a little bit of mixture of analytical, and might as well review the graphical. Now this is optional. If I didn't have a graph space, you could do this problem without the graph, but I'm going to use it as an instructional tool to kind of connect the two analytically, right? So this is a piecewise function. X plus 5 is what kind of graph? Aligned with what 2 characters? Increasing slope of what slope? 1 and a y-intercept, if it had a y-intercept, of 5. Why doesn't it actually have a y-intercept? Yeah, the domain for the piecewise doesn't include that region. So it would want to do this. I was taught to actually draw the thing and then get out the eraser. It actually ends at -2. When x is -2, what is the y value? 3. So it terminates at -2, 3. Open or close circle there? Open. And do I make the arrow to the left or the right of that? Left. Less than -2 is there. Okay, so it's a line stopping at an x, not a y of -2. It stops at x of -2, which is to say it's got a left side and a right side. All right, square root graph. Show me in the air what a square root graph looks like. Okay, what does the 3 do? Shifts it left, right, up, or down?
Right. Oh, no, left.
Left 3. Excellent. Yes, left 3. Good job. 2, actually, generally speaking, adding a number shifts it. Multiplying by a number, what does it do to the graph? To stretch or a shrink, condition. I say squish, but condense, whatever you want to call it. Stretch or squish. In this case, does this stretch the graph or squish the graph horizontally or vertically? So stretch horizontally or vertically? It's a vertical stretch. Well done. Okay. What is the first point on the curve? When you put a -2 in for x, that is the first value of x I can put in. When I put -2 in, what do I get for y? 2. Okay, so my first point is -2, 2. Is that an open or closed circle? Closed circle. All right. What's another good value above -2 that I can put in? 1. Okay. If I put in 1, what do I get? 4. What about another good value? 6. When I put in a 6 for x, what do I get? 6. So I'm seeing that little steeper growing square root function, something like that. And do you agree it does continue on forever to the right, but not the left? Right? Okay. So with that, we could do the problem graphically, but let's do our first option as analytically. So pretend this graph's not there after we spent all that time working for it. If I were doing this limit without a graph to look at, in a piecewise case, you have to decide which piece do I use. This says -2 from the left, or a little less. If I want to see what the function approaches a little less than -2, do I use the line or the square root graph? The line. A little less is this guy, which means I use this. And if I direct substitute in -2, what do I get for y when x approaches -2? 3. Excellent. For q, if x approaches -2 from above, doesn't that mean greater than -2? Greater than -2 is here, which means I use this branch. As x gets closer to -2, what is that graph approach? 2. Excellent. All right. So what about if I asked what is the limit as x approaches -2? Does not exist because whatever that says, 3 does not equal 2. Yeah? All right. What about question R? The limit as x approaches 6 from the left, the right, or whatever, g would approach. Which branch do I use? The bottom one. For a 6, that's greater than -2. I must be saying what's on that graph. So that's more of an indicator. And left or right, be darned, or even the point itself, they're all going to be 6. What about g at -2? Is that the point or the approach? Is that D and E? No, it's not D and E, it's the point itself. And which one contains the point itself? The lower one, and so it is 2. Excellent. All right. Cool. Did that go okay? Any questions there? Excellent. Let's go to something that might not be quite as easy, or I have my expectations for. If you don't have a calculator, would you get out a calculator, please? Or you can borrow one from up here if you like. I'm going to clear my scratch pad. Where's clear scratch pad? How do you clear your scratch pad? What is this? Oh, well. What is the clear scratch pad? Darn it. Is it in here? There it is. Okay. All right. Cool. I'm just going to work from the scratch pad, though you can definitely do a document. Anybody in AP Physics? Okay. All right. Anybody in physics? All right. You're going to have to work out the calculator issue. All right. So the problem is that in physics you use degrees, as far as I know. In calculus you use radians. Period. Never degrees. Never. And so you're going to have possible issues of it. You came to this class for your calculators and degrees, and you dropped an F on my test because your calculator gave a degree as you told me. We'll talk about that as going forward, but I would strongly recommend you either do scratchpad in physics and a document for calculus, or vice versa, or but we'll talk about that later. Just know that that's going to be an issue, degrees versus radians. It won't be an issue until we get to derivatives, but for now, just have that in the back of your mind. All right, so going to this problem here. This is kind of funky. This is an analytical problem in that it's not a graph, but if you actually put 0, oops, that's no problem. This is supposed to be x goes to 0. Sorry, would you change that to x goes to 0, not 6? That's dumb. This is actually one of the most famous limits in all of calculus. There really are 3 super famous limits. Sine of x over x, 1 minus cosine of x over x, and 1 plus 1 over x to the x. All those are limits we're going to have to eventually get down cold, automatically recognized, but later. The problem here is this. If you put 0 in, you get sine of 0. What is sine of 0? Is it 0 or 1? It is 0 over 0, and that's a problem. Let's talk about that. 0 over 0, what is it? It's indeterminate, does not exist, or undefined. Okay, so let's talk about these two, because this is going to be an issue all year long. It's actually, I'm going to do a mini, an algebra 1 quick lesson. Look at this. Say you had 0 over 0 and you said, what is it equal? All right? Do you agree that algebraically I could multiply that 0 over? Now, is there an x that makes that true? Could it be 5? Could it be 7? Could it be -2? So would you agree that there is an x that makes it true, but I have no way of knowing what it is? It could be a lot of things. It can't be determined what it is. I don't know what it is, right? So in that case, then you go more. You go further. This case, 1 over 0, what does it equal? Say I, again, move the 0 over. Is there an x that makes that true? Is there anything times 0 that equals 1? Is there such a number in all the world of numbers? No, there is no such number. This does not exist or undefined. This exists, just don't know what it is. Graphically speaking, what are you looking at when you have a 0 over 0? What's happening at that point? If you get 0 over 0, what's happening at that point? This, for example. It's a whole, yeah. Okay. Because at 3, they would cancel and you're left with x. At 2, they would cancel and you're left with x. At every point, they would cancel and you're left with x. The only difference is at 4, you don't know what's going on. So there's a whole, all right? So when you see 0 over 0, you need to think, oh, no answer. You don't think no answer, you think, oh, I got to do more. There's something going on here. I need to investigate what it's approaching, because there's a hole there, all right? Now, there are a lot of ways to do this. Algebraically speaking, if I could factor or cancel, that'd be great. But these aren't the same kind of x, so I can't cancel those. X in the sine function is not the same as an x not in the sine function, so I can't cancel there. One of the ways around that, then, is to use a table. That's what I want to get you some practice on. This is how I want it done. I would like you to make a table of 2 rows and 8 columns. 1, 2, 3, 4, 5, 6, 7, 8. If you draw 7 lines, you'll get 8 columns. We are going to compare at different x values, what does the function approach. And we're going to put the value we're approaching right in that 5th space, so we can approach 0 from both sides. Some numbers to the left of 0 or less than 0, and some numbers to the right of 0. Now, as a limit problem, then, we want to get closer and closer and closer. Starting further out from the table, we want to get closer and closer. It's tempting for students to say, so you mean like 3, 2, 1? And that makes sense, but that's not a very good way to do a limit problem when you're talking curves, all right? So instead, it's more common that when you construct a table, you go by powers of 10. So you might start 1 away, then get a little closer and go 0.1 away, and then 100th away. And you're getting closer and closer to 0 from above. And then you do the same thing from below. Starting 1 away, but 1 below would be -1, and that's very far away from 0 on the table. Then a little closer to 0 on the table is -0.1, or -0.1, and -0.01. Are you with me? This will be the table you use to justify. Now, the end result is, what is this equal? Now, this doesn't actually exist, but I don't care that the point doesn't exist. It's about what the approach is, right? I'm not looking for the whole. I'm looking for what we're approaching at the whole. So we need to calculate those values. Now, surely I could type in all of this. Sine of 2 times 1 over 4 times 1. Type it in, hit enter. Sine of 2 times 0.1. The quicker way to do this, and that's the part I want to focus on, would be rather than retype all the time over and over again, let's go to the graph menu and define the function. So we could just call up f all the time. So would you type in sine of, was it 2x or sine of 2x or sine of 4x? 2x divided by, in parentheses, is it important that I put parentheses around that 4x? This goes to pre-algebra. If I type it this way, what is it doing with those 4's and x's? It's dividing by 4 and multiplying by x. Is that what you want to do? No, that x is in the numerator right now. It doesn't look like it, but it is. So if you want to divide by that whole thing, it better doggone well be in parentheses. Okay? Now go back. You can hit the graph, and that's great. And if it just said, hey, find the limit, I might use the graph. But it says use a table to justify your answer. And the graph doesn't do it there. You need to use a table. So you're going to go back to the you're going to go back to the home screen, and we're going to recall that function and put in all those values. So for example, you could hit bars, all right? Anytime you want to recall the function in the scratch pad, hit bars, you only have one function in. So that function I just made, I want to evaluate it at, let's go with 1 to start with. And if you hit enter, did you get 0.227 for that function at 1? Record it, please. 0.227. Now, just avoiding retyping all, I'm just going to scroll up, recall that, and throw in a negative in front of it. From the left side, it's also 0.227. That seems to mean that the graph has what around the y-axis? If they're the same on either side of the graph, that's, if my body is the same on either side of a line of, okay, I almost said it for you, there's a line of symmetry. If it's symmetry about the y-axis, what kind of function is that? Even, odd, or negative? Even. Y equals x squared. Okay, so at any rate, record that. 0.227. Here. Cool. Continue. Again, trying to save you some time. On that then, I might go back and just type in a 0.1 or insert a point then and get this one. 0.496. Pause for a second. In terms of decimals, in my class and on the AP test, it's 3 decimals or more, rounded or truncated. 3 decimals or more, rounded or truncated. So if I gave 3 decimals rounded, what would I say? 0.497, rounded to the 3rd decimal place, right? If I said 3 decimals truncated, truncated means chop. If I chop after 3 decimals, then what do I say? 0.496. Both answers would be acceptable in the AP test. What if I gave more than 4 or 3? 0.4966. Is that acceptable? Absolutely. Okay, you must get at least 3 rounded or truncated. So, 0.496. And what about on the negative side? I didn't prove that it was even. I'm thinking it's even, but I could verify that by throwing a negative in there. And it is the same, 0.496. Okay, and then try for the 100th away. Did you get 0.499? Yes? Okay. Now, when you do delta epsilon proofs, that just means you used a delta of 100th, and the epsilon is 1,000th, but we'll talk more about that. Proving limits is a little different exercise than finding limits, but we'll talk about that in set 103. At any rate, what do the y values seem like they're approaching? 0.5 or a half, yeah? Okay, so that, when I say to find a limit justifying with a table, I found the limit that the table is the justification for why I say that, all right? That's the process. Okay, now let's talk analytical, which is the most common limit problems. The majority of limit problems you're going to do are analytical limits. What's the first thing you try? Somebody who's good at limits, what's the first thing you try when you evaluate a limit? Plug it in. The fancy way to say that is direct substitution. If you're plugging it in, then you're going with the assumption that what it is the same at the point is the same as the approach, which means you're assuming what idea? What do you call that when the approach and the point are the same? Continuity. Yeah, you're assuming continuity. Now we'll talk more about continuity tomorrow, but many times functions are continuous, and so it's okay to say, well, I'm going to go with the at, because in this case they're the same. So direct substitution, what do you get for the first? When you direct sub 5 in 26, and what do you get for the second? 2. And do I write the limit in front of that, or is the limit goners? Because now I'm actually doing that limit. It's goners, all right? So our answer is 52. Oui? All right, upon direct substitution here, when you put -4 into the numerator, you get 16 minus 24 plus 8. What is 16 minus 24 plus 8? 0. What do you get in the denominator? Does that mean there is no answer? No, it means we need to investigate further. Now, investigate further, in this case, means do some algebra. What algebra can I do? Factor. When you say factor, what is the numerator factor to? X plus 4, x plus 2. If you're bad at factoring, you need to get good at factoring because that is a huge skill in calculus. Do I still write the limit? Yeah, I haven't put -4 in yet. That means I haven't done the limit yet. It's still there. Now, the beauty of that factoring is that 0 over 0 problem has been removed. Now I can put -4. What do I get? -2. Okay? So you do some algebra to remove the 0 over 0 problem, then do the limit by direct substitution after the problem is resolved. All right, do you agree that in C you have a 0 over 0 problem? Because 5 squared minus 25 would be 0, and 0 is 0. So what algebra can I do in C? Let's go with Emily. Yeah, you can square 5 plus h or FOIL it out. When you square 5 plus h, what do I get, Marcus? Oh, there you go. I thought he was just quiet. Haley Groff.
25 plus h.
Beautiful. Minus 25 over h. Excellent. Matt Hatch, what 2 things could I do to clean this up? Cancel out the 25s or subtract the 25s. When those are gone, what else will I be able to do? Take out the h. And so when I do those both at once, what is the result, Bailey Hutt? 10 plus h. Wonderful. Can I direct substitute now? And if so, what do I get? Andrew? Excellent. Okay. Are we cool? So factoring, foiling, another algebra problem. Look at the back. When you try and direct substitute in D, what happens? Tommy? You have a hole. It's 0 over 0. And so in this case, what algebra can I do? Alex Ludwigson? Oh, hey, I better mark this down. Who else did you say was absent? Marcus. Ludwigson is absent. Marcus. And Nico. Thank you. Yeah, dropping like flies. All right. So, so not Alex Ludwigson. Brian, what algebra can I do here? Multiply by 4x. Beautiful. What if somebody next to you said, oh, I got a common denominator in the top? Is that wrong? It's not wrong. It's mathematically sound. Now, you're going to have a little more work to do. But so what Brian, you're Brian, right? Yeah, what Brian says is the quickest way to do that. If you thought, get a common denominator, it's not wrong. It's just more expedient to say, rather than get the fractions together, let's dump the fractions all together and make our life easier. In other words, eliminate the fraction within a fraction problem. If I do that in the numerator, what do I have? Anybody? 4 minus x. And in the denominator, should I distribute out or leave them separate? Leave it separate. So tempting to cancel. Are they the same? At the heart of that is, does order matter in subtraction? And the answer is, yeah, a little bit. So they're not the same. If I did try and clean it up, what would I do? So they could cancel. Factor out a negative. So I think if we took out a negative, then I'd get an x minus 4 that goes away, and boom, boom, then I can direct substitute. If I put in 4, then I get negative 1/16. Wonderful. All right. All right, so that's a third different algebra. Every one of these last two problems, we had 0 over 0, and we did algebra to work it out, different algebra. What about in E? Wouldn't you agree we get 4 minus 3 is 1, minus 1 in the top, and, or sorry, 0 in the top and 0 in the bottom, so it is the same deal. When you see a root problem, what do? Speak some math to me, baby. Sorry, people? No. And I didn't just call you baby. People? Multiply by the non-reciprocal conjugate. Excellent. Gosh, I love teaching at this school. You guys have amazing basics. All right, so our foundation. So what is the conjugate? 3 plus 1. You're really using the difference of squares factoring pattern in reverse to get squares that eliminate the roots. So wonderful. The limit, do I rewrite the limit or it's not there anymore? It's still there. I haven't actually put 4 in yet. In the numerator, when I distribute, what do I get? X minus 3 minus 1. No roots. And in the denominator, distribute or leave it out, separate. Separate. The reason you don't want to multiply it together is you're going to want to be able to cancel. Do you agree that you're going to get an x minus 4 and an x minus 4? Dropping out, and then you can direct substitute. When you direct substitute, you get 1 over this is a positive, isn't it? 1 over 2. 1 over 2. Thank you. Okay, awesome. Last but not least, f. These two things are together. Keep in mind, that's the function. It's a piecewise function. And the limit. So, are we approaching 4 from the left or the right? Both. Okay. And when we approach from the left, what function do we use? Which, 2 to the x or 10? 2 to the x, the exponential function 2 to the x. When we approach from the right, what do we use? So you're saying we use 2 to the x both times? When do we use 10? At 4. So graphically, what might be happening here? From the left and the right, it's the same function, so they're probably going to approach the same value, right? But what about at 4? It's probably a hole, and that dot that they're putting in, that y value of 10 might be filling the hole, but it might not. We don't know. But that's a continuity question. I don't care. In terms of the limit and from the left and the right, we're using this time, this function each time. So we're really just saying, forget the 10 in this case. That's a problem for continuity tomorrow. For now, just focus on 2 to the x, which approaches 16. Down? Whoa. All righty. Is this the right place in notes? Yeah, sometimes I lose a piece and I just make sure with you. Okay. So, end behavior is a huge idea of calculus. Calculus deals with change. It also deals with the infinitely many and the infinitely small. It deals with infinity a lot. Now, I'll say this over and over all year, but infinity is not a number. It's an idea. Okay, it's like democracy, love. Okay, it's not like 4. It's more of a concept. So in this case here, when I say, what does this huge, gross thing, which I don't even want to get into the graph, that's probably got asymptotes and all this mess, I don't care. All I care about is on the right side of the graph, as x grows without bound, as x gets positively huge, what does all this approach? Now, first thing you need to understand is the idea of a dominant term. Overall in the top, yes, it's x to the fifth and some little stuff, but for infinitely large, that little stuff means less and less, okay? Think of it like a dollar and change. So this is a million and change, a billion and change, a trillion and change. Does change mean jack to a trillion? No, okay? So as x gets large, you focus on the dominant term in the top and ignore all lesser powers. I don't care, okay? They're going to contribute a little something, but not much as x gets large. And this guy here, as x gets large, this is what it's all about. Now, in terms of how those two compare, that's where I get to how the numerator and denominator compare. If the numerator is more powerful, which I think you'll agree in this case it is, because x to the fifth is more powerful than x to the fourth, then the top of the fraction grows bigger faster. If the top grows bigger faster, I erase them all, then what kind of numbers do I approach? Oh, they'll get huge, okay? Huger over smaller is huger. So this is infinity, positive or negative. Think this is huge positive over not as huge positive. So the result is positive, huge. The top wins. And if the top wins, the function goes to infinity. What about e to the x in natural logarithms? Which is more powerful?
E to the x.
If you're a visual person, how does a graph of those two functions help you make that call? What does e to the x look like? That. And what does natural log look like? It's the reflection of that across y equals x. It's the inverse, so it's like that. Now we're focused on, as x goes to infinity, which one has the greater y? Wouldn't you agree that at any x, as we go this way, the y is on the exponential way more than the y is on the log. Way above. Just think above. Okay? So that means e wins. And therefore, because e wins, the top wins, and it goes to infinity, the only question now is sign. Positive or negative infinity? Positive. Both of those y values are positive. Positive divided by positive is positive. All right, and then the last one's a little whack. This one's requires you to do a little more thinking. As x gets really large, what does the top do? It's really large positive, yeah? Positive, large, positive, huge. Doesn't grow as fast as some of these, but it still does get bigger, faster, faster. 5 and 6 and 7 and 7. What about sine? As x goes to infinity, what does sine do? It oscillates. Yeah, wonderful word, oscillates. Well done. Oscillates. Positively or negatively? Both. What kind of numbers? Big numbers or relatively limited numbers? Limited how? 1 to negative 1 or negative 1 to 1. All right, so these are positive and negative, but relatively small. Now, surely the quotient is large, but what about the answer? Do I say positive infinity, negative infinity, or I can't say and I say something else? What should you say? If there is no single thing to say, you say DNE. That's DNE. Okay, so say DNE. If there's not a single answer, then there's no answer. It does not exist. Right? That's DNE. Now you might argue, if a limit is what number the y values approach, and infinity is not a number, doesn't that mean these limits don't exist? And you're absolutely right. In many calc textbooks, you would see DNE for these answers rather than infinity. It's kind of how you think about it and how your textbook goes. I'll say infinity just because I feel like it's more information than DNE here. I feel like this DNE says more than DNE there. So I will use infinity. The good news on the AP test, they will never give you both choices. They wouldn't give you infinity and d and e and e. I wonder which they wouldn't do. Okay? So don't sweat that. Now, the case is, what if the denominator is more powerful? If you have fractions where the denominator is way bigger, what kind of numbers do you get? Big or small? Yeah, when you divide by a huge number, you get a small number. So in this case, the dominant term is 3x to the fifth, and then here the denominator, dominant term is 6x to the sixth, and the x to the sixth wins, so it's going to go to 0, and in that case, then the sign really wouldn't matter, although we're talking positive, so it would be 0 plus, so, you know, it'd be positive small numbers, okay? What about this guy? As x goes to infinity, which one wins? Natural log or y equal x? Which has bigger y values? X, okay? They're not strong, but the log is pretty weak. So if the denominator wins, the denominator goes faster and the fractions go to 0. And last but not least, x cubed and e to the x. Well, which one wins? X cubed seems pretty darn powerful, right? E to the x wins, you're saying? Okay. What about, so you're saying exponential wins. What about, let's take that to the extreme. What about if I took exponential that's super pansy exponential, like this, and this? X to the billion. Which of those ones? The exponential on the top or the polynomial on the bottom? Which one's more powerful? Exponential wins. The top one wins. Now it'll take a while for it to win, but it will win. Okay? Even in the most extreme case, exponential, if the base is more than 1, is more powerful. All right. So in this case, the exponential does win, which means it does go to 0. All right. Cool. Last but not least, what if the powers are the same? I think you'll agree that the dominant term in the numerator and the dominant term in the denominator are the same. And so you're talking 3 billion over 6 billion, 3 trillion and change over 6 trillion and change. Those start to approach just trillions over trillions, and then it's about how the coefficients relate. And so what would this approach? 1/2 or 3/6, okay? If the powers are the same, then the power, the function kind of cancels itself out, and it's just the coefficient. Sometimes you're asked to do a little more thinking. If I ignore the change here, what does that roughly simplify to? The square root of 4x to the 6th. 2x to the 3rd. This is roughly 2x to the 3rd there, yeah? So as x gets infinitely large, I'm looking like 2x to the 3rd and change over x to the 3rd and change. What does that approach? 2. Okay? So again, you can focus on the dominant term, find the greatest power in the top and the bottom, and say, how do they relate? If the greater power is in the top, then it's infinity, or negative infinity. If there are greater powers in the denominator, it's 0. If they're equal power, or equal in order of magnitude, it's the ratio of the coefficients. I think I have time. Would you do these real quick in about 1 minute or so? I'm going to finish taking attendance. All right, you are here. Cole Maxwell, are you here? Lexi? Lily? Aaron? Campbell? Harrison? Tupo? Miranda? Evan? Evan's not here. Okay. So I'm missing Nico Coco, Marcus Garcia, Alex Ludwigson, and Evan Wilson. What? He doesn't? Wow. Okay. Huh. That's something. Is his brother go here? Okay. Guess that's something for talk about another day. I got too much to do now, right? Now to talk about that, but how would I love Okay, will you crank those out real quick? That's terrible. I'm sorry to hear that. 2, 4. Okay. Oops. All right. Sorry to rush you if you're not quite done, but I'm running out of time here. The top one, do you agree your dominant terms are 6x cubed and x squared, greater power on the top, so what does it go to? Infinity or negative infinity? X, negative infinity. That was the first time that you had a sign issue there, negative infinity. Well done. Denominator, is the first term always the greatest power?
No.
You gotta look through and look at for the greatest power and the sign in front of it. So I'm looking at negative 4x to the 5th over x cubed. What does that approach? It's negative infinity. It's negative infinity. Okay, it's negative huge over positive less huge, so that's a negative huge. This one's actually called an indeterminate form, but and we'll talk about more in the future. But what does x go to? As x goes to negative infinity, x goes to negative infinity, which is to say negative huge. What about e to the x? 0, so small positive, yeah? So the question is, which one wins? E or x? E is more powerful, so do I go with negative infinity or 0? It's 0. The e kills the x. All right, and the last one, what do I get there? Which one wins? Exponential wins, so dividing by huger numbers gives me 0 or infinity? Okay. All right, last but not least, infinite discontinuities. Vertical asymptotes. When you get something like 0 in the denominator, you're talking a vertical asymptote. It doesn't have to be 1 in top, it could be any non-zero number in top, but it's a vertical asymptote. So in this case, for example, if you approach 1 from the right, then you're getting, think of it like 100, 1 and 100. If I take 1 and 100th minus 1, I'm left with 100th in the denominator. What's 1 divided by 100? 100. Then I get a little closer, 1 and a millionth. 1 and a millionth minus 1 is 1 millionth in the denominator. 1 over a millionth is a million. So you're getting huger and huger. This approaches infinity. What about from the left-hand side? When you divide by tiny numbers, you get huge results, but positive or negative? Negative. And therefore, the limit at 1, if the limits are different from either side, it must be infinity. Okay? So what about e? If we approach 2 from the right, then we're a little above 2, so it's positive, but we're approaching 0, so we're looking at infinity positive. What about the next one? 2 minus x is like 2 minus 2.1. Was that positive or negative? That's negative. Small in the denominator. 1 over small negative is huge negative. It's negative. What about this guy? 1 divided by, yeah, they're small numbers and they're negative, but they're being squared. So overall, what's the result there? Infinity or negative infinity? Infinity. And the last one. This factors, x, how's this factor? X minus 7, and that sign is important, x minus 5. Do you agree? So is that a whole? It's not a whole. It's not 0 over 0. It's non-zero over 0, and that's a vertical asymptote, right? Which means it's infinity or negative infinity. So now the question is, which one? Well, if I'm a little less than negative 7, then what's negative, like negative 7.1? Do you agree? Do you agree that's less than negative 7? Okay, so negative 7.1 plus 7 is negative or positive? Negative. Okay, so this is negative. What about negative 7.1 minus 7? Negative, and negative 7.1 minus 5? So I have 3 negatives. So what do I say?
Please rise for the Pledge of Allegiance.
Okay.
Please begin. I
I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Will you please tell us going too slow?
Calling all Beverly Student Clubs and sports teams interested by